So today we'll be talking about symmetry. So in particular, crystallographic symmetry. We're showing the differences in the different types of symmetry you can have, such as some of them are familiar, like rotational axes, mirror planes, inversion centers, but we also will have some that are crystallographic symmetry, such as glide planes, which is a collection of mirror plane and translation, and then also screw axes, which is also a combination of rotation and translation. So we're going to talk about how do we perform these operators and to generate a new set of coordinates. So we'll go ahead and get started this afternoon. So the last week we talked mainly about lattice and motif, or lattice and motif. This week we're going to be talking about symmetry and space groups, and also how do we get the asymmetric unit. So to kind of explain how all of this builds up, the asymmetric unit is the unique portion for the entire crystal. So from the asymmetric unit, you use symmetry to generate everything in the unit cell. And then once you generate all the symmetry equivalent molecules or entities in the unit cell, then that unit cell gets translated in 3 dimensions to make the crystal. So whenever you solve a crystal structure, what you're solving is what's called the asymmetric unit. And we'll talk more about that later on. And so by knowing the symmetry, we're able to classify crystals or crystal structures in different types of groups based on what symmetry is present. So that's why symmetry is important when you're dealing with crystal structures. In addition to that, we can determine the type of crystal system and if there's any centering as well. We'll talk also about what a space symmetry element is too. So this is why symmetry is important, because it helps us identify space groups. And so when we're talking about symmetry, symmetry means that when we perform a certain operation on a set of coordinates, it leaves it indistinguishable from its original state. And when we perform this movement, it's called a symmetry operation. So a symmetry operation is when you take the symmetry and you perform it on the object or coordinates. The symmetry element is the type of symmetry it is, whether it's about a point, such as in an inversion center, a line, when it's about a rotational axis, or a plane, which is in reference to mirror planes. And that's a symmetry element. So a twofold parallel to C, for example, is a symmetry element. It becomes an operation when you perform that element on a particular object or set of coordinates. And so that's the difference between element and operation. So we'll be talking about symmetry elements when you perform those elements, those movements on a particular object, then it becomes a symmetry operation. That's the only difference between the two. Element is the actual symmetry. The symmetry operations when you perform that element on an object or set of coordinates. So there are different types of symmetry we can have. Some of these, if you've taken, I think, descriptive inorganic or inorganic chemistry, you've at least heard of point symmetry. And with point symmetry, we have infold rotations, we have reflections, we have inversions, roto-inversions, and identity. We still have those same type of symmetry elements in crystallographic symmetry as well. So if you learn those in descriptive or in inorganic chemistry, it's the same type of operation, just a slightly different notation that we use, and we'll see that in just a little bit. So all the point symmetries are still valid in crystallographic symmetry. So we'll see we'll have some infold rotations, we'll have reflections, of course inversion center. Now, roto inversion centers we don't see unless it's a very high symmetry space group, but we do have those that occur as well. It's a rotation followed by an inversion, and of course the identity. So all of those are the same from what you learned with point symmetry. Where it becomes different is when we introduce space symmetry. So space symmetry means we combine point symmetry, such as an infold rotation, with translation along a particular axis. And so with space symmetry, we have centering, so we can shift the center of a set of coordinates off the origin. So we translate along one of the axes or multiple axes. We have screw axis, which is a rotation followed by a translation parallel to the rotational axis. So for example, just to give you a kind of illustration of this, a screw axis, the notation will be written as 2 sub 1, so the 1 should be a subscript, parallel to B. So what this means, and we'll learn about this in just a moment, 2 sub 1 parallel to B is a screw axis, which means you do a twofold rotation about the B axis or the Y coordinate, and you then translate a half a unit along the B direction, aka the Y coordinate. So it's a rotation and then a translation. So whatever axes you rotate about, you translate over on the other axis. And then a glide plane is a reflection followed by a translation. And we have different ones. We have the face glide planes, which is an A glide perpendicular to B. So what that would mean is you would reflect in the BC plane, and then you would translate along the B axis. And we'll talk more about those in just a minute. But these are additional, what we call space symmetries. So it's combining point symmetry and translation. So in point symmetry, you learned about Schnoffele's notation, which describes the symmetry within a molecule. So that's what point symmetry does. And make sure you make that distinction that this describes symmetry in a molecule. And we learned the point symmetry. Now with crystals, we talk about Hermann-Malguin notation. And this describes symmetry in crystals. So notice the difference. Schnoffele's notation describes symmetry in a molecule. Hermann-Malguin notation will describe symmetry in a crystal. Sometimes they overlap, sometimes they do not. And so Hermann-Malguin notation combines both point symmetry and space symmetry in their notations. And so when you have space groups, they combine these different types of symmetry. So here, for example, C2 upon C, the capital C means that it was what we refer to as C-centered. The 2 upon C means a twofold parallel to the B-axis, and then a C-glide perpendicular to the B-axis. So by the time we finish space groups, you'll understand how to extract all the symmetry operators from a space group notation. So again, the capital C or capital P or capital I denotes the type of centering. So if it's capital C, it's C-centered. Capital P is primitive, which is the center is at the origin. And capital I is body-centered, just to give you a few examples. So always listed first is the centering, and then you have the symmetry elements. And so since C2 upon C is monoclinic, everything is around the B axis. So this twofold rotation is parallel to the B axis. So we have a twofold parallel to the B, and then we have a C glide perpendicular to the B axis. And that's how you would interpret the space group symbols for C2 upon C. So that's the symmetry operators that are shown in this space group notation. Now later on we'll learn how we combine those to generate other symmetry operators. So whether you're in the monoclinic system or orthorhombic or tetragonal system, there are different unique axes. So for example, monoclinic, the unique axis is the B axis. So anytime you have a symmetry element, it's always about the B axis. Now in orthorhombic, you'll notice we have three different operators. Because in orthorhombic, you have the A axis, the B axis, and the C axis. So when we talk about space groups, we're going to be talking about the unique axes in space groups, and that's what shows up when we're talking about symmetry elements. So for monoclinic, all the symmetry elements are about the B axis. To show you the slight differences in notation that we use for the different types of symmetry elements. So from, descriptive or inorganic chemistry, when we talk about point symmetry, a rotational axis is C upon N. So if a twofold would be C2. However, with Hermann-Malguin, when we have a twofold, we just write the number 2. That's a twofold rotation. And typically, as you'll see, you'll include it in, you'll also include the axis about which you rotate about. For mirror planes, for point symmetry, they use a sigma. For Hermann-Malguin, we use an M. Inversion center, point symmetry, we use I. For Hermann-Malguin, we use what's called 1 bar, or a line on top of the 1. Improper rotation, we just use, we don't have really a symmetry for improper rotation. That's only unique for point symmetry, so there's none for crystallographic. Roto-inversion center, which is a rotation followed by inversion center. You would just write the rotation and then you put a bar on top of it indicating an inversion. And notice that point symmetry does not have roto-inversion symmetry. Of course, the identity, which is just 1. Now all of these, from identity to rotational axis, are point symmetry. Now below, when we have centering to glide planes, this is going to be space symmetry. So it means there's translation and a symmetry operation. So centering means we shift the origin from 0, 0, 0 to some other coordinate. Now if it's centered along the A axis or the BC plane, then the center would be, for example, 0.5, 0, 0. So A, B, and C are your face centering, I is body centering, and F is all the faces. So it's centered on each of the faces. That's face centering. A, B, and C are just individual faces that it's centered. Then we have screw axes, which is a rotation followed by a translation. So it's going to be, for example, 2 sub 1 is a rotation, a twofold rotation followed by a 1/2 translation. And then we have glide planes as well. So A glide perpendicular to B. So it means you reflect along the, we'll talk more about that in just a second. So today we're going to talk a little bit about rotation and mirror planes, but we're going to spend a lot of time on screw axes and glide planes because that's crystallographic symmetry. So with rotational symmetry, we have anywhere from 1-fold rotation where we have 360 degrees up to a 8-fold rotation, which is 45 degrees. And note here on this, the second bullet, this is very important, that all of these are permitted for molecules. So if you have a molecule, all of these are allowed rotations. And remember this, because this is important when we talk about unit cells and crystallographic symmetry. We'll come back to this. So remember, for molecules, any of these rotations are permitted. And they have different symbols that you may see along in the molecule, or for example in the unit cell, that describes the different types of rotational symmetry. So typically when we're drawing the symmetry operators or symmetry elements, so here we would show that this represents a twofold symmetry about this point where you generate a new set of coordinates through a twofold. And so they usually in unit cells, they draw this to show you where in the unit cell the symmetry element is located, or symmetry operator is located. So it could be located in the center of the unit cell. It could also be located on the cell axis. So for example, here, you could have a twofold rotation, etc. So it can be located anywhere in the unit cell, but about this rotational axis, you rotate, you generate a new set of coordinates. And since this is this symbol here, this represents a twofold rotation. So we have, triangles for threefold, squares symbolizes fourfold, 6 is a hexagonal looking rotational symbol. So you will see these, and if you've used Mercury yet, when you do your Mercury assignment, you'll see the different symmetry elements pop up where they're located in the unit cell. So for example, there's a twofold rotation here. There's also going to be a twofold rotation here and a twofold rotation here as well. So every unit cell will have the twofold rotation located in the same position. So you can have also in crystallographic or unit cells, you can have symmetry within a molecule. So for example, here water has a twofold rotation about this axis here. And this organometallic complex has a twofold shown along the dashed line. So in unit cells, you can see the twofold within a molecule, or it could be in a portion of space somewhere in the unit cell. It doesn't have to be within a molecule. So here when we look at this molecule here, we may say, well, what type of rotational symmetry is present within this molecule? And you may say, well, based on this, it looks like you should have a twofold and a sixfold rotation. However, the twofold and sixfold is not present here because these molecules are distinguishable once the symmetry operation is applied. So you see we have one pointing down in this area. It's not the exact same thing. If we look here and here, these are different. So they're distinguishable. So it wouldn't have twofold or sixfold symmetry. It would actually have a threefold symmetry within it. So that triangle here represents that this molecule has threefold symmetry. Now you may say, well, can't molecules have multiple rotational axes? Yes, that's correct. So you could have multiple types of rotations in a molecule or within a unit cell, but they only consider the one that's the highest in the principal rotational axis. So if you had a twofold and a fourfold, the fourfold would be the one that gets counted because it's the highest principal rotational axis in the molecule or in the crystal. So when you perform rotational symmetry, what you're doing is you're helping fill the space within a unit cell. That space could be molecules, it could be atoms, whatever. But when you do this symmetry operation, you're filling space in that unit cell. So if we have a unit cell, what you start with is the asymmetric unit. So this is the asymmetric unit. Call it ASU. And so the asymmetric unit is the basic building block to build all the symmetry equivalent positions inside the unit cell. So if this unit cell had rotational symmetry, you would use rotational symmetry to generate the rest of the molecules or atoms that are related by that particular rotational symmetry. And then once you build that entire box with all the molecules, then you have the replica of the unit cell that can be translated in 3 dimensions. And so again, when you solve a crystal structure, what you're solving is the asymmetric unit, the basic component, this basic region of space that you need to generate all the other symmetry equivalent positions in that unit cell. Now with crystallographic symmetry, there are only certain types of rotational symmetry that can fill 3-dimensional space. So not every type of rotation is allowed in crystallographic symmetry. So only these types of rotations can fill 3-dimensional space. So notice there's no 5-fold or 7-fold or 8-fold rotation when we're talking about crystallographic symmetry. It's only 1, 2, 3, 4, and 6 rotational axes are permitted in crystallographic symmetry. So you'll never see a unit cell with a 5-fold rotation or a 9-fold or 8-fold rotation. Only these types of rotations are allowed because they fill space. Because again, the rotational symmetry element doesn't have to be located within a molecule. It can be located in a region of space somewhere in the unit cell. So in our little example here on the top right hand, if I was to draw a 2-fold rotational axis here, it doesn't occupy a molecule or atom's position. It occupies a region of space, and then we generate the symmetry equivalent portion of space on the other side of the 2-fold rotation. So again, this rotational symmetry is based on what symmetry the lattice points possess. So each one of these coordinates is a set of lattice points in your unit cell. So once we have one lattice point, we can use symmetry to generate the other lattice points in the unit cell. Now, one thing that is quite common that people try to do is based on the symmetry of the molecule, they try to infer what type of symmetry the crystal can have. Now, this is actually not a very good thing to do. I mean, you can get some insight about the crystal symmetry based on the molecule symmetry, but just because the molecule has a 2-fold symmetry within it, for example, doesn't mean that you would see 2-fold symmetry in the crystal, because the way the molecules crystallize in the unit cell or in the crystal will dictate what type of symmetry it has. So sometimes it may follow the symmetry that you see in the molecule, other times it may not. It just depends on the crystallization conditions as to what type of crystallographic symmetry appears. So just because your molecule has 2-fold symmetry doesn't necessarily mean that the crystal will have 2-fold symmetry. Because again, the molecule is its own entity. The crystal is when all the molecules crystallize, or you could say freeze, as they become a solid. So depending on how the crystallization conditions are, you may or may not have that rotational symmetry. And this goes for any type of symmetry you find within a molecule. It doesn't necessarily correlate to symmetry you'll see in a crystal. So when we apply symmetry operations to fractional coordinates, we're generating these symmetry equivalent fractional coordinates. So once we know the symmetry related coordinates, it can help us identify equivalent positions. So we can say by looking at a set of coordinates that these two coordinates are related by a 2-fold rotation. The second important thing is it allows us to generate general positions within the structure. So we can say at this particular set of coordinates, if we do a 2-fold, we can generate the other set of symmetry related coordinates. And by applying these symmetry operations, we can also see what other symmetry elements are there. So when you look at a space group, the space group is like the short form of symmetry elements. It only gives you the minimum number of elements so that you can generate all the different molecules in the unit cell. But when you start, for example, when you take a screw axis and a glide plane and you combine them together, you get actually a third symmetry element. So by combining symmetry elements, you generate new symmetry elements. And so when you have all the symmetry operators, you can see which ones you can combine to generate other types of symmetry. So to give you an example, if you have a twofold rotation plus a mirror plane, I should say a twofold rotation parallel to B and a mirror plane perpendicular to B. Let me draw the correct symbol for mirror plane. When you add these two sets of operators, you generate an inversion center. So if you take a set of coordinates, perform a twofold rotation parallel to B, and then on that same set of coordinates do a mirror plane perpendicular to B, you'll generate what's called an inversion center. So that means there's a point in space where you go from the positive coordinates to the negative. So for example, if we start here with coordinates x, y, and z, we perform our twofold rotation along B. That means that we get negative x, y, negative z. Then we perform a mirror plane perpendicular to B. That means that the B axis becomes negative, so that becomes negative x, negative y, negative z. And so you see when we do a twofold parallel to B and then do a mirror plane perpendicular to B, by combining those two symmetry elements, we get an inversion center. So anytime you take a rotation followed by a mirror plane in the same, so rotation parallel to one axis and the mirror plane is perpendicular to that same axis, you're going to generate a set of coordinates that are the inversion center. And so that's how, by knowing some of the operators or elements, you can generate the other elements. So again, we start with some general coordinates x, y, and z, twofold parallel to B. What that means is that the y coordinate doesn't change, only the x and z become negative. Then a mirror plane perpendicular to B means that the mirror plane is perpendicular to the B axis, so that's the one that becomes negative. So it's like the AC plane you reflect through, and that makes the y negative. So an inversion center is when you make a set of coordinates the negative of what you started with. And we'll show you more about this when we talk about space groups a little bit later on. So just like I talked about, it allows us to identify inversion centers as well once we know all the symmetry elements. So now let's look at a twofold rotation. A twofold is usually parallel to one of the axes. And so for a monoclinic system, that twofold is always going to be perpendicular to the B axis. So anytime you see a monoclinic space group and you see a twofold in that space group, it's always going to be perpendicular to the B axis. But just to show you here, if we have just imagine that the B axis or the Y axis is coming out towards you in the out of the screen. So we have a set of coordinates x, y, and z. If we rotate it 180 degrees, what happens is we get negative z and negative x. but y still remains the same because y is the axis about which we're rotating about. So the y coordinate doesn't change when we do a twofold rotation. Now, you can either write it as negative x, y, negative z, or common in crystallographic symmetries, we put x bar, y, z bar. So the bar indicates that it's negative. So you'll see both ways, but the bottom way is the common practice with crystallographic coordinates, but either way is acceptable. So let's say we have a set of coordinates. We say 0.2, 0.55, and 0.80. And we want to perform a twofold parallel to B. So since it's parallel to the B axis, only the x and z coordinates will become negative. So our new set of coordinates is negative 0.2, 0.55, negative 0.8. Now the cool thing about rotational axes is if you keep on rotating, you'll eventually come back to where you started. So we did one twofold rotation. We got these symmetry equivalent positions. Now you may ask, but what happens if we do another twofold rotation? So if we do another twofold rotation, we just become back where we started. And so the way you know you're doing twofold rotation correctly is if you keep on, or any type of rotational operation correctly, is when you keep on doing the rotation, eventually you come back to where you start. So if you were to do a rotational operation and you keep on doing it, you never come back to where you started, that's a good indication that you probably made a mistake in one of your symmetry equivalent positions. So a twofold rotation has two symmetry equivalent positions: the original coordinate and the symmetry related coordinate. Notice again that y value does not change because we're parallel to the b axis. Now if you wanted to say how would this look if we were parallel to the c axis, so we can look at that. So we take the same set of coordinates, but here we'll do it a twofold parallel to the c axis. So since we're parallel to the c axis, the z value does not change. So then it would be negative 0.2, negative 0.55, 0.8. So again, whatever axis you're parallel to, that coordinate doesn't change sign. So if you're parallel to the a axis, then the x value doesn't change. If you're parallel to the b axis, the y value doesn't change sign. This is regardless of what type of rotation it is. If you're parallel to any of these axes, those values do not change sign. Now, if the c axis, if you're parallel to the c axis, the z values does not change sign. So anytime you have a rotational axis, if whatever axis it's parallel to, that particular fractional coordinate will not change. It will stay the same value as you do all your symmetry operations. Give you just a moment to kind of look over that. Okay, so that's a twofold rotation. Twofold is easy. It's just two of the coordinates become negative, and we do a twofold. Now, when we look at a fourfold rotation, fourfold rotation is a little bit different. It's not as straightforward. And so what we have to look at is fourfold rotation means that we rotate 90 degrees each time. And for simplistic purposes, and also because it's common practice, is that we're just going to stick to a fourfold rotation parallel to the z-axis. And the reason we're going to do this is because fourfold rotation appears in the tetragonal space group where the primary axis is the z-axis. So any type of fourfold rotation is going to be a fourfold parallel to the z-axis. So what you can imagine is that the z-axis is coming out of the screen and you're kind of rotating it about the z-axis. So you're kind of moving the axes counterclockwise 90 degrees each time. And so if we look here, we start with a set of coordinates. We start with the coordinates x, y, and z. And we rotate it 90 degrees counterclockwise. So what happens is, when we do that, the new x is the negative of the previous y, and then x, z. So notice how x and y change positions, but the new x is actually negative y. So it's and I'll show you an example of this. So if we have a set of coordinates, say this is 0.3, 0.2, 0.3. When we do the first rotation, so what you do is the new x is the negative of the old y. So this becomes negative 0.2, 0.3, 0.3. So let me label this as 1, this as 2. So this is our first coordinate. This is our second set of symmetry related coordinates. So again, notice all I did was the new x, when we rotate it 90 degrees, is negative of the original y. So we take the negative of the y, that becomes our new x. So our new x is negative 0.2. Our new y is the previous one's x, becomes 0.3. And then of course z doesn't change because we're parallel to the z-axis. Now if we take this coordinate here and rotate it again 90 degrees counterclockwise, so we take here and we move it, we're going to end up in the third quadrant, which is right here. And so if we're comparing this set of coordinates to the previous coordinates, now we get that the new set is negative x, negative y, z. So what we're doing is each time we're taking the negative of the y, making it the x value, and we're taking the previous x value and making it the y value. So I know it's confusing. So here, if we want to generate the third set of coordinates, we take the negative of the x of our original x and the negative of the original y to get the new set of coordinates. So it would look like this. Let me show you. Let's see. So negative x, negative y. I think it's negative 0.2. Negative 0.3 and 0.3. So our previous x, which was negative 0.2, excuse me, no. So So we look at, let's see, hold on a second. Okay, yeah, let's scratch this. Hold on 1 second. So here we take our previous x value, and our previous x value becomes negative x. So our previous x value was negative 0.2. So if we make it negative now, so we take the previous x and make it negative, it becomes 0.2. Because again, we take our previous x value, which is negative 0.2, make it negative, it becomes 0.2. And we take our previous y value and we make it negative, it becomes negative 0.3. And then z doesn't change. So actually, let's see. So that would be the third set of data. Negative 0.2, 0.3, 0.3. Rotated. Negative x. Negative 0.2. I'm missing one here. Let's see. Let me write it on paper real quick. Three, okay. And then negative y, negative 0.3. Okay, okay. I got it cleared up now. Let's see. We'll just start again. So our original coordinates, say, is 0.3, 0.2, 0.3. The operator that we're going to do each time is negative y x z. So each time we do this, we're going to be taking the negative y x z. So when we do that, the new x is the negative of the y, the negative 0.2, 0.3, 0.2. That's 190-degree rotation. That puts us right here. So this is number 2. Number 2. Number 1. Now we're going to take that same set of coordinates, and again, we're going to perform a 90-degree rotation. And so again, we're going to do this again, negative y x z. So we take the new x is the negative of the y, so that'd be negative 0.3, negative 0.2, 0.2. And so that will put us in the third quadrant right here. Then we're going to do another fourfold rotation, so this is 0.3. We're going to do another 90-degree rotation. So again, we're going to do another negative y, x, z. So we're going to take the new x is the negative of the y, so it's going to be 0.2, negative 0.3. This shouldn't be a negative here. 0.2. And 0.3. Rewrite that one. So negative 0.3, negative 0.2, 0.3. And so this is the fourth position here. Now if we do one more fourfold rotation, again, we're going to take our previous set of coordinates and we're going to do a negative y, x, z operation. That's fourfold rotation. So when we do that, we get 0.3, 0.2, 0.3. And notice that that's the same as the original set of coordinates that we started with. So this is the same as our initial. So we made a full 360 degrees. Now what you're seeing here at the bottom is, if we're just starting from the original set of coordinates, here we get 0.3, 0.2, 0.3. Now with our original set of coordinates, if we do negative y, so with what's shown at the bottom, you always start with your original set of coordinates. So here we would have, if we're starting with the original set, it'd be negative 0.3, negative 0.2, 0.3. And then the last one would be 0.2, negative 0.3, 0.3. I'm sorry, the z should always be 0.3 for all of them. Let me correct that. There should be a 3 here. So if you're doing the operation one at a time, then you always use the previous set of coordinates. So if you were doing a fourfold rotation and you just want to do negative y, x, z each time, you would do it the top way. If you already had all the operators and you just want to do the coordinates, well, what's on the bottom, you have to start with your original set of coordinates each time. So to get this, the second set of coordinates, you would just take the negative y of your original coordinates, make that x, and then x becomes the new y. And then for the third coordinate, you would take your original coordinates and use that to generate the third set of coordinates. So that's the difference between the top route and the bottom route. The top route is you're doing the same operation, just you're using the previous coordinates to generate the new set of coordinates. Either way is fine. It doesn't matter which way you choose, just pick one. So now let's look at some examples. So here we have the following set of coordinates. We want to perform a twofold parallel to C, a twofold parallel to B, and a fourfold parallel to C. So we want to generate all the symmetry related coordinates for this. So when we have a twofold parallel to C, we start with 0.3, 0.4, 0.75. We do a twofold parallel to C. That means C remains constant, it doesn't change sign, only A and B change signs. So negative 0.3, negative 0.4, 0.75. Now, if we were to do this twofold one more time, you would see we would end up back at our original starting point. So we get 0.3, 0.4, 0.75. And so this has two unique positions, the first position and then the second position. Now if we look at a twofold parallel to B, so we have 0.3, 0.4, 0.75. Since it's parallel to B, that means the Y value does not change. So we get negative 0.3, 0.4, negative 0.75. Now if we were to do this twofold again on that set of coordinates, we would get 0.3, 0.4, 0.75. So again, for a twofold, there's only two unique symmetry positions. Now for a fourfold, so we have 0.3, 0.4, 0.75, and this is parallel to the C axis. So remember, for fourfold, the basic operation is negative y x z. So each time you're going to take the negative of the y and make that the x, and then the x becomes the y. And you do that 4 times. So we have negative 0.4, 0.3, 0.75. We do it again. Again, we take the negative of our previous y value, negative 0.3, negative 0.4, 0.75. And then we do it again. So 0.4, negative 0.3, 0.75. So again, every time I'm just taking the previous set of coordinates. To get the new x, it's the negative of the previous y, and the new y is the previous x value. And so if I do it one more time, I get 0.3, 0.4, 0.75. So we start back at the origin, or the original position. So there are 4 symmetry-related sets of coordinates. And so this is how you perform a twofold and fourfold. I'm not sure if threefold, we'll talk about it today or will be tomorrow, but threefold is a little bit different, but it's a similar type of process for the fourfold. It has a different symmetry element, but it's the same thing you do. But after 3 rotations, you end up back at where you started. So this is how you do a twofold and a fourfold rotation. It's very important that for a fourfold rotation, you remember this operator. This is very important. So for a fourfold rotation, you're always going to be doing this operation. Now for a twofold parallel to C, if you're curious about that, the operator is negative x, negative y, z. And for a twofold parallel to B, it's negative x, y, negative z. So that's rotational axes. Again, threefold and sixfold, either we'll touch on it today or for sure tomorrow. We'll look at threefold and sixfold rotation. Now we're going to talk about mirror symmetry. So with mirror symmetry, we have a reflection across a plane. So rotational symmetry, if you didn't pick up on it, it's a rotation about an axis. So since you have a rotation about an axis, if you think of 3 dimensions, an axis is only 1 dimension. That means when you have a rotational axis, 2 coordinates are going to become negative because an axis is 1 dimension, like the y-axis or the z-axis or the x-axis. With mirror symmetry, symmetry is a mirror across a plane. So you reflect across a plane to generate a new set of reflected positions. Now, Since it's a plane is 2 dimensions. So when you have a reflection, usually you say it's perpendicular to the B axis. That means it's in the AC plane, and the B coordinate is what gets reflected. So that's what becomes negative. So mirror symmetry involves planes. So it could be the AC plane, it could be the BC plane, or the AB plane. And again, for mirror symmetry, only one coordinate becomes negative. So if we have a mirror plane perpendicular to B, so if that was our symmetry element, then we would have X, Y, Z. If we do a mirror plane perpendicular to B, it would become X negative Y, Z. So notice here, for mirror planes, only one coordinate becomes negative. For axes, if you picked up on it, 2 coordinates become negative because an axis is 1 dimension. So that means only one coordinate is not going to change. Whereas a mirror plane, since it's 2 dimensions, a plane, that means 2 coordinates aren't going to change, only one of them. So whenever you say a mirror plane perpendicular to an axis, whatever axis it's perpendicular to is the one that's going to change sign. So it could be that you could have a mirror plane on a molecule, so you would have a reflection, it would generate the other half of the mirror plane or the molecule. It could also be that the mirror plane is in a region of space, so you would reflect another molecule to generate the other part of the symmetry equivalent positions. Now, if we apply a mirror operation twice, we would come back to where we started with. So we look at our top example. Now, if we take those symmetry related positions and do another mirror plane perpendicular to B, you notice that we come back to the original set of coordinates. So if you do a mirror plane twice, you're going to end up back at where you started with. And so with Schnoffler's symmetry, when we talk about mirror planes, usually we would say it's a vertical, diagonal, or horizontal mirror plane, and we do like sigma sub h, sigma sub v, sigma sub d. But with Hermann-Malguin, if it's a mirror plane, typically we say mirror plane perpendicular to C. Now, we do have other types of mirror planes that include different notations. So for example, we could have, as we'll see later on, mirror planes with translations that have slightly different symbolism. So instead of saying a mirror plane, you would say, for example, an A glide perpendicular to C. So the perpendicular to C means that you make the C negative and you translate along the A. So we'll talk about that a little bit later on. But for Hermann-Malguin, this is the notation that we use for mirror planes. We say mirror plane perpendicular to some axis. And that axis that you're perpendicular to is what becomes a negative coordinate in your set of fractional coordinates. So again, you can have mirror planes within molecules, you can have mirror planes within molecules or in regions of space. So it just depends on which mirror plane you're referring to. So before we get to the inversion center, let me do a few more examples with mirror planes. See if I can find a place to do some work. So before we start talking about inversion center, I'm going to do some examples with mirror planes. So we're going to look at a mirror plane perpendicular to A mirror plane perpendicular to B, and a mirror plane perpendicular to C on the following set of coordinates. So we have these fractional coordinates. And we want to perform the following operations on this set of coordinates. So we want to do a mirror plane perpendicular to A. So since it's a mirror plane perpendicular to A, that tells you that the only coordinate that's going to change signs is the x coordinate. So it'll be negative 0.4, 0.3, 0.2. So that's the resulting set of coordinates when you have a mirror plane perpendicular to A. When you have a mirror plane perpendicular to B, since it's perpendicular to B, B coordinate is the one that's going to become negative. So it'll be 0.4, comma, negative 0.3, 0.2. So the thing you should see here is that whatever axis you're perpendicular to, that's the coordinate that's going to become negative. And then a mirror plane perpendicular to C, since we're perpendicular to C, only that one becomes negative. So mirror planes are fairly straightforward. A mirror plane perpendicular to A, to B, and to C. So all you're doing is whatever axis is perpendicular to, you just make that coordinate negative. Mirror planes, fairly straightforward. Now what we're going to talk about now is inversion symmetry. And this is very important to pick up on, because when you have inversion or you don't have an inversion center, this can change the properties of your crystal. And so an inversion center symmetry is based on a point. So if you notice here, rotational axes are along one dimension, an axis. Mirror planes are along a plane which is 2 dimensions. So only one becomes negative. Now with inversion centers, it's about a point. So there's some region, a point in space where you take a set of coordinates, it becomes a negative of those coordinates. So for inversion center, all the coordinates become negative. So if you have the coordinates x, y, and z, the inversion center would just be negative x, negative y, negative z. That's it. And so remember this, because this will come up quite often, is that crystals or crystal structures with inversion centers are referred to as centrosymmetric. Whenever you hear the term centrosymmetric, it means that one of the symmetry elements is an inversion center. So again, centrosymmetric means that one of the symmetry elements is an inversion center. And later on in the week, when we talk about space groups, we'll talk about which space groups are centrosymmetric, meaning those space groups have an inversion center. So when we talk about centrosymmetric, we're not just simply referring to one molecule. We're talking about the entire crystal. So there's an inversion center somewhere in the crystal that helps generate the other inverted set of coordinates. So it can't just be a molecule that determines the inversion, it's the entire crystal. So there are certain space groups that will always have a inversion center in it. It's always going to be centrosymmetric. So if something is centrosymmetric, it's always going to be centrosymmetric regardless of the molecules that are in it. Just to give you a little prequel of what's to come when we talk about space groups, these are some space groups that always have inversion centers in it, and we'll talk about that later on. But there's 3 examples of centrosymmetric space groups. And so anytime you have something that crystallizes in these 3 space groups, it's always going to have an inversion center. It doesn't matter the type of molecule. it's always going to be in a centrosymmetric space group. And I forgot an M in centrosymmetric, but you can put it in. So again, anytime a space group is centrosymmetric, regardless of the molecule, it's always going to have an inversion center. So to give you a little bit of background on this, let's say you have a chiral molecule and it crystallizes in a centrosymmetric space group. What that tells you is that it's not a pure enantiomer, it's a racemic mixture of both enantiomers present. If it was not a centrosymmetric space group, so typically sometimes with chiral compounds, if it's enantiomerically pure, it will not be centrosymmetric because it only has one of the enantiomers in the sample. And so that would be in a non-centrosymmetric space group. So again, centrosymmetric means there's an inversion center located in that series of symmetry elements for that particular space group. It does not depend on the molecule, just depends on the set of symmetry elements in that space group. Oops, yeah. So here again we have different types of symmetry equivalent positions. So in the first example, you see that there's a center of inversion right here. So as we go through this point, we get our inverted set of coordinates. So this S1 and that S1, they're just inverted with one another. So again, inversion centers are through a point. So for this one, even atoms can sit on inversion centers. So in the example to the lower right, this sulfur goes through an inversion center to generate the inverted structure. So you go through a point to generate the inverted set of coordinates. So these structures here would be in centrosymmetric space groups. So space groups that contain a symmetry element that is one of them, which is a inversion center. So how does it change the fractional coordinates when we have an inversion center? Again, we start with x, y, and z. All you do is you make x, y, and z negative. So we get negative x, negative y, negative z. And what it's showing you here is the difference between a twofold rotation and a inversion center. And so if we applied a twofold along C or along Z instead of inversion center, you see the coordinates would be different. So that means that this open circle is a different height than the closed circle. So for inversion centers, again, all the fractional coordinates become negative. And this one has an inversion center at the origin right here. So you go through the origin, you generate the inverted set of coordinates. And so you don't have to have it at the origin. You can have inversion centers off the origin. And so here's just showing you, for example, if we have an atom at 0.25, 0.25, 0.25, oops. So here, if this one has an inversion center at the origin, that means that the inverted set of coordinates would be at negative 0.25, negative 0.25, negative 0.25. But since these are all negative coordinates, if we translate by 3/4 in each direction, that tells us there also must be a inversion center at 0.5, 0.5, and 0.5. So again, this is replicated throughout the unit cell. So that's if it's at the origin. If it's not at the origin, you can have different types of inversion centers. So if we have an inversion center at a half minus x, a half minus y, a half minus z, that means we have an inversion center at 0.25, 0.25, 0.25. So the inversion center would be halfway between the two sets of coordinates. So 0.5 minus 0 divided by 2 gives you 0.25. Whereas here on the left-hand side, 0.25 plus a negative 0.25, that's 0. So that tells us the origin is at 0, and it can also be, if you do 0.25 plus negative 0.25 or minus 0.25 becomes 0.5. So you can have inversion centers at the origin, in the middle of the unit cell, or anywhere along the unit cell. So when you just have X, Y, and Z, the atom is at the origin. But if you have an inversion center at 0.5 minus X, 0.5 minus Z, 0.5 minus Y, the inversion center is off the origin. So let me just show you one example of that. So let's say we have an inversion center at 0.5 minus X, negative Y, negative Z. And we start with the set of coordinates. Let's say we have an atom at 0.25, and we perform this inversion center, we get, let's see, 0.5 minus 3.25, negative 0.25, negative 0.25. So this would be the set of inverted coordinates for that one. And this would tell you that the inversion center is off of the origin. Because if you were to find the midpoint between these 2 points, it wouldn't be at the origin 0, 0. So long story short is, you can have inversion centers that are not on the origin. So why are centrosymmetric crystals important? Because whether it's centrosymmetric or non-centrosymmetric, it can affect the properties that these crystals have. So non-centrosymmetric crystals or crystal structures have a variety of different types of properties. They could have, referring to polarity, chirality, optical activity, etc. And just because you think, you may see inversion center in a structure, just the slightest differences in the bond distances and bond angles, or even changing the elements, can break up the inversion center. So if you don't have good quality single crystal data, and it causes your bond distances not to be very accurate, that could affect whether or not you have a inversion center or not. So, very slight differences in these types of things, such as bond distances and angles, can affect whether something has inversion symmetry or not. So on that note, we'll stop here for today. And on Tuesday, tomorrow, we'll pick up with roto inversion symmetry, and also screw axis space symmetry and glide plane space symmetry. And then we'll also touch on 3-fold and 6-fold rotations. So that's what we'll be picking up with tomorrow. So that's all I have for today. Now I'll take some of your questions if you have it.